Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Flex Logix with Geoff Tate, who's going to talk today about the MLPerf benchmarks. Geoff, there are a lot of benchmarks out there, but what's the actual relevance of MLPerf for the edge?
Edge computing is where you're not in a data center. You might be in a server, say in the back of a Walmart or a Wells Fargo. You might be in a surveillance camera. You might be in a car. And the needs of edge computing are very different from data centers. The MLPerf benchmarks that were recently published for inference are pretty much server-centric. If you go to the website, you'll see a list of products. You'll see 5 different benchmarks like ResNet 50. And you'll see within each benchmark 4 different columns, which are a little confusing at first until you think it through. One is offline. Offline is basically giant batch sizes. So not relevant to the edge, maybe relevant to data centers. And that's where you'll see the highest performance. Another is a server case where they have some random Poisson distribution of request inter-arrivals not relevant to the edge. Then there's multi-stream, where you might have multiple different independent streams of requests coming into an inference accelerator in a data center environment, probably not relevant to most edge applications. And then there is stream. And stream is getting close to edge computing. Stream is where you measure the performance with a single inference request at a time for that particular benchmark.
Why don't you draw this out for us?
Okay. And in the stream mode, there is a host processor. And the host is communicating with the inference processor or coprocessor.
So how exactly are those measured?
Well, the way MLPerf has set this up is their benchmark is measuring the latency under the following conditions. So it's for a particular model, ResNet 50 version 1.5, 224 by 224. And something to note is that 4 out of the 5 of the benchmarks are for very small image sizes, which are generally unrealistic for edge applications. In the edge, you want to be at a megapixel. Only one of these 5 benchmarks is at a megapixel resolution.
The edge also spans from the end device all the way into the servers that are on-prem, right?
Edge is anything that's not in a data center. So there are a lot of servers that exist in enterprises, banks. They may be hooked up today to surveillance cameras capturing digital data. In the future, they'll process that data using inference as well. And there is inference like in a surveillance camera, a doorbell, etc.
So let's go back a little bit. How does MLPerf actually measure inferencing?
Okay, well, remember, they had 4 different metrics. We discussed that 3 of them are completely irrelevant for the edge. The one that is relevant to the edge, but not really what you want, in my opinion, is stream mode. So in stream mode, the host sends an image to the inference processor, 1 image, and it waits until it receives the results back. At that point, you measure the latency in milliseconds from sending the image to receiving the results, with some caveats.
And those caveats are what?
Those caveats are, first, for whatever reason, the DRAM load time is not counted in the latency. Not clear why, because in a real system, the DRAM has to get loaded. Also, things like cache warm-up time is not included in the latency. It's not clear what that entails, and it'll depend on a processor. But it's 1 image at a time. But the other biggest issue is that it's at a 90th percentile. So it's the latency at which 90% of the requests are met. So if you had a bell curve distribution, say the result that you got was 10 milliseconds for a particular chip, you don't know what the distribution is of the latency requests. All you know is that 10 milliseconds means that 90% of the latencies were less than 10 milliseconds and 10% were over 10 milliseconds.
And a lot of the AI, machine learning, edge chips, the inferencing chips, are pretty much one-off type of chips, right? So they're used for a specific application. It's hard to say this is going to be a benchmark that's going to span all of them.
Well, that's why they picked 5. But whether these 5 are representative of edge applications or not is another issue, but at least they have 5. Because if you pick one, it could be you build a chip that's fantastic for that, but useless for everything else.
And this is still missing things like power at this point, right? So you can't really compare, particularly on the edge, where you may worry about things like power. How much power does this consume in doing this operation versus a different chip?
Yeah, I saw an article after MLPerf came out talking about the winners. But you can't determine who the winners are based just on the throughput numbers, because it could be that one chip has the same throughput as another, but one costs $1,000 and the other costs $10. One's 1,000 watts, the other one's 10 watts. You can't tell. All it gives is the performance, not the power or the cost.
Did this happen in other markets as well? When you look at, say, CPU market of years ago, wasn't that part of what drove a lot of that market, is you actually could make apples-to-apples types of comparisons?
Well, in all of these markets, comparing products gets to be complicated, and in the CPU market, it started off with just simply megahertz. Back in the old days, processors didn't run at gigahertz. And then people eventually realized, hey, we have to come up with workloads. We have to have stuff that involves the memory subsystem, not just the processor. But if you were a graphics person, you'd have a very different workload than if you were a database person. So the same thing will happen in the inference space. But at the edge, just coming back to this 90th percentile, the most important thing about this is that can you really design your edge system based on the 90th percentile latency, or do you need to know the absolute worst case latency, and how long is that tail? And that's something you cannot tell from the MLPerf benchmarks. In our experience, customers need to know the worst case, the 100th percentile, not the 90th percentile.
So is it easier to make benchmarks in the edge than it would be in the data center, or the other way around?
In a data center, you have to run multiple workloads, and those workloads will change in the future. And if you're Facebook, you're probably running a very different set of workloads than if you're Amazon or if you're Microsoft. So each of those data centers is going to want to look at a range of benchmarks representative of their needs, and there isn't going to be one benchmark that dominates everything else. But at the edge, when you're looking at any given company, at least what we see, is customers are wanting to run one model. And they know what the model is, they know what they need in terms of latency and batch size, they know what image size they need. So for them, life is simple. Vendor A, B, C, D, run my model, tell me the throughput, and how much does it cost, and what's the power.
And the trade-offs here are those same three things, right? It's performance, power, and basically area/cost.
Yes, when we talk with customers, every customer has a power envelope they have to work within. Some may be 100 watts, some may be 5 watts. And every customer has a cost budget that they have to work in as well, and they have a latency or throughput target that they're trying to achieve. And generally what they want is to get the best performance they can within their constraints.
Do any of the other factors, such as environmental impact on these designs, affect any of these benchmarks as well? So you think about an automobile, for example, and it's a very harsh condition. If you have an inferencing processor in that car, it's going to be a lot different than if you have an inferencing processor in your house.
Well, sure, or take a more obvious example of a surveillance camera. If the same surveillance camera sitting in this conference room, where it's kept within narrow temperature bands, has a very different thermal challenge than a surveillance camera sitting outside a Walmart facing the sun in Phoenix, Arizona in the summertime.
You have to calculate that into your benchmarks as well, because it's no longer just a simple this chip versus this chip, it's this chip in this application.
And so that's a good point. If you look at some of the chips that were in this study, for example, the NVIDIA Jetson Xavier AGX, it's a very long name. When you dig in, you find out that their module is limited to 90 degrees junction temperature. whereas typically chips in a data center are running at 105. So it means that you have to be that much more careful about the thermal environment that you put it in. And the reason there's limitations is if it ran at 100 degrees, it would be burning more power, it would run slower, there'd be something that would be an issue at that point. So again, there's some fine print that you have to check, not just the throughput. And not just the power numbers, you need to know the exact operating conditions for those power numbers.
Is there any benchmarking at this point in terms of longevity of these chips? How long will they be reliable over time?
These chips are just coming out, so there's no benchmarking in the sense that they've been in production for 10 years. And this industry is going to change so fast, nobody's going to be in production of the same chip in 3 years. They'll all move to better process nodes. But we're at a point in time in the semiconductor industry where there's very reliable information provided by the foundries. So we get a PDK from the foundries, a process design kit. It's like 1,000 pages long, and it has lots of formulas and guidelines as to how to compute reliability that all of us use in the industry, and we all benefit from that.
And this is basically their simulations and saying, here's how it should perform over time, right?
Yes, everything grades over time. And so depending on what your application is, if you want something to be like in a satellite for 30 years, you're going to push things differently than if you're designing something that's, say, in a product that's going to be obsolete in 3 years. Like most cell phones aren't in use 3 to 5 years down the road. So people know what they're designing for, and the more that you're designing for longevity, the more you're going to back off on frequency, you're going to reduce operating temperature, because all of the fundamentals of what can go wrong in a chip get worse as you have higher temperatures and higher frequencies.
Does your memory and how it's connected make a big difference as well?
In inference, definitely. A lot of people are talking about needing HBM memories. High bandwidth memories, or HBM2. So these are monster DRAM devices that will sit on top of the silicon chip and connect directly without being in separate packages. The idea there is to give much, much more bandwidth. If you look at chips from NVIDIA and Habana Labs today, they have 8 DRAMs, 256-bit buses. So these people are going to go to HBM memories and integrate them into the package, but it's very expensive. But it allows you to get higher frequency. Some of us are taking another direction, which is to minimize memory to get high performance. And I think in the end, for the bulk of the market, that is going to be the winning solution.
So do these benchmarks, should they be set as this is the chip functioning in the context of other chips and other systems, or should it be just the chip itself?
Inference is a nice, tightly contained thing, so it's reasonable to benchmark the inference chip separately from everything else in the system, and that's what the customers want to know. They take care of the rest of the stuff, like if you're in a car, if you have an inference chip telling you where pedestrians and bikes and so forth are, somebody has to decide what to do about that. That's a different chip and a different set of software. So inference is nice and tidy, you can benchmark it separately, and that's the right approach to do it.
But your latency is now a function of where is that chip in relation to something else too, right?
Yeah, at a system level, latency isn't just the inference chip latency, it's a total latency. So if you're in a self-driving car, there will be a spec, and that spec will be from the input to the camera to the time that you start taking any action about what you're seeing. That's going to be a certain number of milliseconds, and the inference is part of it. Capturing the image is part, cleaning up the image is part, processing it through an inference processor is part, and then there's some decision engine that decides, oh, that pedestrian is moving in front of me, I have to slow down, I have to move, whatever.
So what you're doing with the benchmarks here is really focusing on a specific application and not how it connects to everything else. It's how fast it processes that, whatever your workload is.
Correct. And then the system designer knows the latencies through the other parts of their system, and they can figure out the end-to-end latency.
Geoff Tate, thanks for a great explanation.
Oh, thanks, Ed.